All right, and welcome back. We are now in part two of our Routes to Chaos series. And what we wound up talking about last time was kind of an introduction to what's known as symbolic dynamics. Right, we are passing the problem of dynamics on the or in the logistic equation or logistic map rather to a completely different problem in a completely different phase space. And the symbolic part of the dynamics here is because we have two symbols to work with. We're working with ones and zeros. So we are taking a problem about dynamics of the logistic map and mapping them into a problem about the dynamics on a sequence space. And we defined that sequence space last time. We talked about metrics on binary sequences, or a metric on the binary sequences. And this one, we had to make it a little more contrived than our usual notions of like Pythagorean theorem distances, or generalized Pythagorean theorem distances, right? These two norms. We necessarily had to change up that usual definition because these sequence spaces are not a natural subset of Rn. In fact, they're infinite dimensional. Sequence spaces are infinite dimensional. And the idea here is that we need to make sure that whatever metric we come up with needs to address every single component of a sequence and then guarantee a convergence on those comparisons. And that's where we wound up with this box, this red box, telling us that here's what we're going to take to be our notion of distance on our sequence spaces, or specifically on our binary sequence. Right, there is a way to measure how far apart two sequences are in this infinite dimensional space. Right, and what we're going to do in this second part of the series, we are going to no pun intended, second part of the series. Okay, what we are going to do in this second part is start establishing this transferal of properties from lambda, this set of non-escaping points in our logistic map, to these properties about sequence spaces, and then showing that they're actually the same in a topological sense. So, as our first lemma, we need to establish that there's something interesting that can be said about sequences that are no more than a certain distance apart. And the first part of this lemma says that if your two sequences agree on the first n terms, or technically n plus 1 terms, then the distance between those two sequences in sigma is no greater than 1 over 2 to the n. That part we can actually see very quickly. Right, if I go back to my definition of a distance, I'm going to go ahead and split it up into two pieces, right? The first n plus 1 terms, and then the remaining infinitely many terms, the remaining tail, right? But if these two sequences are the same on the first n plus 1 terms, then the distance between those component-wise entries is 0. They are the same entry, which means that this tail that I wind up with can be no greater than if everything was different between the two sequences from n plus 1 on. And we can actually see very quickly that this is, once again, a geometric sequence, or a geometric series, which sums up to 1 over 2 to the n. So if our two sequences only differ after n plus 1 terms, then the greatest that those two could be apart the greatest that those two sequences could be apart by in sigma is 1 over 2 to the n. And then we get a partial converse to this, that if the distance is strictly smaller than 1 over 2 to the n, right, I'm going to number 2 here in the lemma, if the distance is strictly smaller than 1 over 2 to the n, then that means that these sequences have to agree up to the nth term, or the n plus 1 term, I suppose. Right, and the way to see this is by going through contrapositive. So suppose that these guys did differ for some element, right? They were different for some entry in the first 0 through n indices. Right? It doesn't even have to be multiple entries. It could just be one. They could be off by 1. But the point is that at a particular entry here, this sk, that these guys necessarily contribute a factor of 1 over 2 to the k to that distance. Everything else, who cares? Who cares about the remaining elements? The fact is that this guy has to be at least 1 over 2 to the k apart from these two sequences S and T have to be at least 1 over 2 to the k apart, and because n is an upper bound for k, that means that these guys have to be no closer than 1 over 2 to the n. Right? They can't be. They can't be any closer because of this 1 over 2 to the k that's sitting in front. Right? So it contributes at least that much, which means that these two sequences would have to differ in some element, some index from 0 to n. Therefore, since we showed for this, we were trying to prove P implies Q here, but we showed not Q implies not P, but mathematical logic shows that these two expressions are actually logically equivalent. So we did, in fact, show the correct proposition that if these two sequences have a distance strictly less than 1 over 2 to the n, then they have to agree for the first 0 through n indices. All right, so that establishes a notion of closeness. It tells us a good idea of what the geometry of this space looks like, right? So we can actually start to measure open sets. We can start creating an idea of what an open set looks like inside of sigma, right? And we need open sets, right? The reason being is that continuity is defined by open sets, right? Continuity says that the preimage of open sets is open. A function is continuous if the preimages of open sets are still open. And we need continuity to construct a homeomorphism, which is why we had to put a metric on sigma in the first place. Right? We could have just made it a straight up topological space, but it's a lot simpler to look at these guys as metric spaces. Right? It's a lot more definite for us. It's easier for us to make the analysis or to do the analysis. Right? But in order to construct a homeomorphism, we need to construct a map that is continuous, or it's a bijection. So that means that this guy is forward. This map is a function in both the forward and backward directions, and it's bicontinuous. It is continuous in the forward and backwards directions. Right? So it gives us a one-to-one and onto correspondence between the open sets of lambda and of sigma. So this is where we're trying to go. We want to show this homeomorphism. We want to create this homeomorphism. So our final lemma is to show that the intervals I0 and I1 that we looked at upstairs are actually expanded by the logistic map, but only if this factor of r is large enough. So the lemma says that if r is greater than 2 plus root 5, then the dilation factor is bounded below by some number that's greater than 1. Right? That's what this k is doing here. It says that doesn't matter if it's a positive or negative value, but if it's greater than 1 in magnitude, then we effectively have something that is expanding the intervals. Right? It's expanding space nearby. Right? This is comparable to looking at our divergence of a vector field and saying the divergence is positive means that volumes tend to expand in certain areas, or if it's negative, then they tend to contract, like we saw in the Lorentz map. But our proof here goes very, very quickly, actually, showing that this guy is going to expand certain areas. We just recall that the 2 points, x plus and x minus, where the parabola of the logistic map extends above the xn plus 1 equals 1 line, we're going to go ahead and compute the derivatives at those points. So you can do this directly, and it's actually not terrible to have to compute on your own. And you can see that those derivatives are given by plus or minus square root of r times r minus 4. And now you can see why we're dealing with r greater than 4. Right? We need to make sure that the dilation factor is actually a real number here. It's not terribly important, but it's pretty helpful. Yeah. Anyway, the idea is that this inequality, in order for that to be satisfied on the total interval here, the inequality actually has to be satisfied on x plus and x minus themselves, right? Because this function has a greater slope. So the slope is largest on this parabola on these two intervals from on I0 and I1 at these two locations. The slope is smallest there, and it only increases down the sides or decreases. So that means the absolute value is only going to get larger from there. So we just need to establish that the derivative is of a particular size on x plus and x minus. And when we do that, we can actually, again, do this directly. The absolute value of that derivative is the square root of r times r minus 4. Solve that with a quadratic formula, and you'll see exactly that your r either has to be smaller than 2 minus root 5, which is actually a negative number, or r has to be greater than 2 plus root 5. And that's exactly where that number comes from. So we're just trying to make sure that our derivative satisfies this dilation property, that the intervals want to get larger, or they want to expand on I0 and I1. And now to the coup de grace. The claim here is that the map that we came up with before, the identification between elements of lambda and elements of the binary sequence space, is actually a homeomorphism when r is greater than 2 plus root 5. Okay, so the homeomorphism that we're looking for is actually the identifying function, the thing that tells us how to go from lambda on the closed interval from 0 to 1 to a sequence in sigma. Right? It's this idea the idea of telling us where each iteration of that point falls, or where its pre-image falls in where its image falls after a certain number of iterations of the logistic map. So it should be noted here that we can actually show that this itinerary map is a homeomorphism for any r greater than 4, but the analysis does get a bit more complicated. So for right now, take it on faith that this itinerary map actually is a homeomorphism when r is greater than 4. But our analysis is going to be sufficient right now to show this when r is greater than 2 plus root 5. So there are 4 things that we have to show to establish that this map is a homeomorphism. So we need to show that this is a bijection, so it means it's got to be a one-to-one and onto function. And it must be bicontinuous, which means that both S and S inverse are continuous. Right? So feel free to pause the video and check out those definitions. Those are standard definitions in math curriculum. Yes, you should know them if you're a math major, right, or applied math major. Right? These are extraordinarily ubiquitous ideas, and you should tuck them away in the back corners of the back recesses of your mathematical knowledge. You should know them. But now that you're back from pausing the video, we can go ahead and check each one of these in turn. So first, we're going to establish injectivity. So we're going to establish that S is a one-to-one map. So let's go ahead and suppose that S maps both X and Y to the same location. Right? I get the same sequence for these 2 points, X and Y, living in lambda. We want to show that X and Y actually have to be the same point. So let's argue this to the contrary. Let's see what happens if we get the same itinerary for 2 different points. Right? Then for each n, these 2 guys are going to lie on the same side of 1/2. In fact, they're going to lie on the same side of the A0 subset. Why? Because they have the same itinerary. They have to lie on the same side of the A0 interval. Great. And notice that the derivative here, partial f, partial x, doesn't change signs on either of those 2 intervals. So f is actually monotone there. And in particular, f is monotone on the intervals that are bounded by the nth iterate of x and the nth iterate of y. So these intervals, remember, x and y aren't at the same point, so they're going to get different orbits on lambda, which means that these in intervals are composed of more than just a single point. Now, because of the fact that we're using r greater than 2 plus root 5, our lemma actually shows that in, each one of these guys, has to expand as n goes to infinity. And because k is greater than 1 as a uniform lower bound here, we're going to keep exponentially expanding that distance, right? And in fact, the distance between the nth iterates of x and y has to actually grow without bound. So that means that eventually that distance is going to be greater than 1/2. And in fact, it should be pretty close to, it's going to get to whatever distance you need. But the idea is that eventually you're going to have to span where the nth iterate of x actually has to lie on the opposite side of the nth iterate of y. So the opposite side of a0, because the distance between them has to be so large, which means that they no longer have the same itinerary. They eventually have to go to different sides of a0. And that means the itineraries differ, which means that we contradict the fact that they had the same itinerary. Therefore, these two guys actually have to be the same. X and y have to be the same location. So the only way you're going to get to the same itinerary is if you came from the same point. So for each itinerary that we can get to, for each itinerary there is a unique point that is sent to that itinerary. So there's 1-to-1. Now we want to show onto. I'll show it back on the screen real quick so you can pause if you want to. That's what we have to show. So for a closed interval j sitting inside of I, and I here is going to be from 0 to 1. So I should actually write that in here. I equals 0 to 1. So we're going to go ahead and let f to the minus n of j denote the pre-image of this. Well, it's not the pre-image. This is going to be, it is. It's going to be all the elements whose nth iterate eventually, or nth iterate lands in j. So this is the nth pre-image of the interval j. So now suppose that we have a sequence in our set of binary sequences. We want to show that for any one of these sequences, there is an x in lambda that maps to it, that has that particular itinerary. So to that end, we're going to define some smaller sets, some progressively larger sets here, or progressively more restrictive sets, I should say. And we're going to say this I sub S0, S1 out to Sn is going to be all of the points in the interval that are in either I0 or I1, and whose pre-image is on a particular side of A0, and whose second pre-image is on the S2 side, and whose third pre-image is on the S3 side. So the S's, S0, S1 out to Sn, these are going to be partial sequences of 1s and 0s. So what we're really doing is we are making smaller and smaller sets, or progressively smaller sets, to say that what am I trying to say? We are making progressively smaller subsets so that we can home in on one particular element and say that this x is the guy that maps to this particular itinerary. And the big crux here to the argument is the fact that these guys are nesting inside of one another, right? That these intervals get smaller and smaller and smaller and are still closed, because this is we haven't established it yet, but we will show that this is an open mapping, a continuous open mapping. But so these intervals keep nesting inside one another. So it is a well-known theorem, or well-known fact, that the intersection of a sequence of closed nested intervals is non-empty. Right? So we're not restricting ourselves out of a set here. Like there's always going to be something in that limiting term. And this is what I'm going to deem as I sub s down here. I sub s is going to be the limiting object, and that limiting object is non-empty. So there is at least one thing in lambda that satisfies that maps to this particular itinerary. It has to go to each one of these sides, each side of A0 in a particular way, as described by these pre-images. Therefore, this function s is also onto. So we have now established that lambda and sigma are in bijection with one another. They have the same cardinality, the same number of elements. Now, we want to show continuity. So notice first that is, right, the thing that we're saying is composed of a point, right? There is something in there that maps to a particular itinerary. But that set is consists of a single point due to the fact that s is 1-to-1, right? If there is, if this guy maps to an itinerary, which we just showed it did, then it's the only thing that maps to that itinerary. So the lengths of these successively smaller nested intervals must tend to 0. They have to get small enough to the point where they only contribute a single point in the limiting object. So what we're going to do, we're going to take that information with us as we go further and say, let's go ahead and choose a location in lambda and let epsilon be bigger than 0. Right? We're trying to show an epsilon delta proof of continuity. So we're going to choose n so large that 1/2 to the n is less than whatever that epsilon is. Right? And you feel free to choose whatever epsilon you want. 5 to the minus 5, 10 to the minus Google, or 1/a Google. Sure, whatever you want it to be. Archimedes' principle says that I can find an n so large that 1/2 to the n is smaller than that epsilon. Consider all possible sets, all possible n plus 1 sequences, binary sequences here. All those sets that we got from upstairs here, all the pre-images. There are 2 to the n plus 1 of them, of which our particular truncation here has to be. So this I sub S0 to S1 out to Sn has to get down to a particular size. And in particular, we can choose delta so small that saying that I'm in lambda and that I'm within delta of this particular x, right? He's got a particular itinerary associated with him, and that's the s that I'm talking about. That those two properties alone imply that y has to be in this particular interval. So that means that s of x and s of y agree in their first n plus 1 terms. We had a lemma that said what happened to the distance when you are when you are the same up to the first n plus 1 elements, the n plus 1 terms. Our lemma said that the distance between the two itineraries associated with x and y can't be any greater than 1/2 to the n, which is what we chose to be less than epsilon. Awesome. So that means that s is continuous in the forward direction. Now we need to show that s inverse is continuous. So choose an itinerary or choose a particular sigma here. And that guy is going to be associated with a particular x value. We're going to go ahead and let epsilon be greater than 0. Again, choose it to be whatever you'd like. Go ahead. See if I care. Choose n so large that the length of the interval, this I sub S0, S1 out to Sn, is less than epsilon. This is possible due to our acknowledgement in the previous part that the lengths of these intervals have to tend to 0 as n goes to infinity. So as above, we're going to choose delta so small that any other sequence t0, t1, t2 out to infinity, and being of a distance less than delta, implies that I'm in the pre-image of this itinerary of all the is that right? T is in pre-image. No, that should be a Y. Is that right? So the pre-image of that, yeah, that should be a Y. Anyway, such that I'm in any one of these guys that's within that has the same itinerary up to the first n plus 1 elements, n plus 1 terms of the sequence. Therefore, the pre-images of S and T must both lie inside I sub S0, S1 out to Sn, and by our choice of n, we're choosing n so large that the length of that interval is actually less than epsilon, actually did that work for us. We're all done. By our choice of n, this interval is no longer than epsilon, so that means that the distance between those two pre-images of the itineraries can't be greater than epsilon, which means S inverse is open, or it's a continuous map as well. All right, this video is very, very technical, so I'm going to go ahead and say that we're done for right now, and that's not at all because I haven't written any notes for the next section, so don't worry about that. The takeaway message that you should get out of the video here and the previous one is that the two sets, lambda and sigma, these two metric spaces, are topologically indistinguishable from one another. They behave exactly the same way from a continuity standpoint. Therefore, whatever dynamics we see on lambda are actually equivalent to the dynamics that we're going to see on sigma. And in the next video, we're going to talk about the dynamics that we see on sigma because we can directly relate that back to the dynamics on lambda. So we're going to show that the shift map is chaotic on sigma, and therefore our dynamics that we see from the logistic map are chaotic on lambda. All right, so until then, right, study hard. This one was not an easy lecture at all, so take some time with it, wrestle with it. Right, it's not necessarily gonna stick with you overnight. So feel free, study it for half an hour, then take a break, come back to it. All right, let it process. It's gonna take some time, but until we get over to chaotic shifting, right? You know what?